Welcome back, junior associates. In our last session, we stood in awe of the Hubble Telescope of Mass Spectrometry, the FTICR. It is a majestic instrument, reaching the 6th decimal place with massive superconducting magnets. But from a management perspective, it's prohibitively expensive and requires specialized facilities. But what if the real revolution didn't happen by making magnets bigger? What if we didn't need magnets at all to achieve ultimate precision? Welcome to Module 8-2, the Benchtop King. Today, we discuss the democratization of high-resolution power, moving high-performance discovery from specialized bunkers right onto your lab bench. Think of the Orbitrap as the high-end mirrorless camera of mass spec. Years ago, professional photography required massive rigs and darkrooms. Today, a mirrorless camera captures incredible raw data, with a sensor the size of a postage stamp. The Orbitrap is exactly that, for our lab. In management consulting, we call this a strategic disruption. By replacing the massive magnetic field of the FTICR with a clever electrostatic trap, Alexander Makarov and his team redefined the market standard. They brought ultra-high resolution out of the basement and onto the benchtop. We aren't losing power, we are gaining agility. To master the Orbitrap, you must understand the 3 pillars that hold up its crown. First, we have electrostatic trapping, the shift from magnetic force to pure electric fields. Second, we have harmonic axial oscillation, the specific dance the ions perform that gives us our data. And third, we have image current detection, the non-destructive way we listen to the ions. This framework allows the Orbitrap to dominate the Omics fields. It offers a unique blend of analytical fidelity and operational ease, providing the resolution to distinguish between nearly identical molecules in a standard lab workflow. When you look at an Orbitrap, you aren't looking at a long flight tube. It looks like a metallic egg or a spindle, deceptively simple hardware that is mathematically profound. At the center, we have an inner spindle electrode, surrounded by a barrel-shaped outer electrode split into 2 halves. Here is the secret sauce. There are no magnets and no liquid helium. The entire mechanism relies on electrostatic trapping. We apply high voltage to that central spindle to create a hyperstable electric field. Ions are trapped in a stable orbit by pure electricity, balancing electrostatic attraction against their own centrifugal force. Now let's look at the dance. Most people assume ions just go in circles, but the Orbitrap is more sophisticated. Because of the egg shape of the electrodes, ions perform a complex 3-dimensional waltz. They orbit the spindle, while oscillating back and forth along the central axis. We call this harmonic oscillation. Think of a pendulum. No matter how hard you push it, its frequency stays remarkably stable. In the Orbitrap, this axial movement is perfectly harmonic. This is a massive strategic advantage, because the frequency is independent of the ion's initial energy. It only depends on the ion's identity. In an Orbitrap, our reliable metric is the frequency of the axial swing. Much like the FTICR, we don't measure mass directly. We measure the frequency of that back and forth movement. Because the electric field is precisely shaped, the frequency, omega, is proportional to the square root of 1 over the m/z ratio. This means heavy ions swing slowly, while light ions swing fast. This is the analytical fidelity that makes the Orbitrap so powerful. By turning a mass problem into a clock problem, we can determine mass down to those legendary 6 decimal places right on your benchtop. So how do we see this swing? We listen to it. The outer electrode is split into 2 halves. As the packet of charged ions swings toward 1 half, it pulls electrons into that plate. As it swings back, the electrons follow. This creates a tiny oscillating current called an image current. Just like the FTICR, we aren't destroying the ions. We are listening to their electrical song. This non-destructive process allows us to record the signal over a long period for higher resolution. We then use the Fourier-Transform to take that chaotic choir of frequencies and pull them apart into a high-resolution mass spectrum. Why did the Orbitrap become the market standard for proteomics and metabolomics? It offers 3 major efficiency gains. First, analytical fidelity. You get FTICR resolution in a package that fits your lab space. Second, high dynamic range. You can hear both the quietest and loudest singers in the choir, allowing you to find a tiny biomarker sitting next to a massive protein peak. Third, the total cost of ownership. No liquid helium, no facility upgrades, and no specialized magnet training. You get world-class discovery power with operational ease. That is why the Orbitrap is the workhorse of personalized medicine. Let's think like an analytical strategist. Imagine a pharmaceutical startup has a dirty sample, and needs sixth decimal precision. They are choosing between a massive FTICR facility or a benchtop Orbitrap. The Orbitrap is the strategic choice because they get the precision without the helium and shielding. Furthermore, harmonic oscillation protects their data integrity. Because the frequency is independent of the ion's energy, they don't have to worry about sample variability ruining their resolution. By understanding the swing of the ion, you know how to leverage high-res power for real-world success. Let's wrap up this briefing. The benchtop king uses electrostatic trapping, electricity, not magnets, to catch ions. The central spindle electrode creates a field that forces ions into a harmonic axial oscillation. We listen to the image current and use the Fourier-Transform to build our data. Here is my golden quote for you. In science, the best technology isn't just the most powerful, it's the one that brings that power to your fingertips. But knowing the mass is only half the battle. To truly understand a molecule, you have to shatter it. In our next unit, Module 8-3, Tandem Power, we learn how to break these ions apart. I'll see you there.